to say this. Something, this was brought to my attention that, like with these quizzes, if you make a wrong answer early on, it affects the latter answers. And I want to say this. I'm not trying to do something that's, you might say, hard on students. What I tried to do in the first two questions, just give you softballs where you're going to get them no matter what. And then the latter part is where you have to build more complicated things. I did give some extra credit. If you know, each one of these technically is worth 2.5 points if you do it right. But I gotta say, when I thought about this type of a quiz here is a very basic quiz. It's like a couple of resistors in series with a battery and ask for current. There's nothing here that's deep, that's really complicated. But the only real way I know to prevent silly errors is to do several problems, do a bunch of problems and come in and be very focused, like, you know, your money's involved in it. Because if you come in here casual and just take this, you can really do bad. Now we're going to move into some stuff that's going to get a lot more complicated very shortly. Did everybody have time to look at the quiz solutions? I don't know if I need to go over these, but I will if I do. And if anybody has individual questions, see me afterwards. Well, this is one of those things. I don't know whether I should go over them or not, but we can if you want to. Real quick. So for this one, for the first problem, let's see. I'm just going to go through it quickly. If you got a question, just tell me. You got two possibilities. You have heads and tails, and this is an even distribution, even likelihood, so they're each 1/2. That's the probability of this. And then if, you correct me on something, heads is rolled, one die is thrown, is that right? All right, so this one, you got one die, and if it tails, there's 2 die. So that's sort of like a typical problem. As a matter of fact, we did a problem, I believe in class, just like this, and I think it was for 3, not 4, I think. All right, now I was trying to make sure that at least I covered it one time in its entirety. But I tell you this much, it is very easy to make a stupid mistake if you're not like on high alert. And I see this, not just here, but you're going to see later on, especially when things get a lot more complicated. You can just almost fall off the wagon so easily in these problems because you can go the wrong way and it destroys everything. I'm just trying to encourage you, but I don't know what else to say. I'm just asking you this. How many think it's fair, that test, quiz? I mean, if you don't, let me know, because I try to make this just reflect the homework. That's all it is. This is not the real difficult stuff. Anyway, for this, the first part, A, was what? And there's a couple ways. It's almost too obvious. It asks what? If a head is rolled, right? So we're assuming a head is rolled. And what's the probability of a 4 given a head is rolled? Right? Now for that one, I think common sense almost drives this one more so than Bayes' theorem. Some people force themselves to go Bayes, and you can. And the solution has it. So if a head is rolled, only 1 dice is thrown. And everything is assuming it's, you know, a fair die, fair coin. So probability of a head or tail is 1/2. Probability of any value on the die is going to be 1/6, right? So because a head is rolled, there's only 1 die. This has to be 1/6. The actual probability of this, of a 4 given that 1 die, is going to be 1/6. Is there any question about that at all? Now we could do it. You can do it with Bayes, right? You could say, well, the probability I have the probability of a heads rolled and a 4 times probability of a head roll is equal to, in this case, probability of a 4 times probability a head given a 4 was rolled. Do you all agree with that, class? And you can go ahead and do this, so we want probability for head. Well, in this case, when you look at this, the probability of a head is 1/2. The probability of a 4, and that's where you get into this, when you can have 1 or 2 die, right? So for 1 die, the probability would be, for 1 die, the probability of a 4 would just be 1/6. For 2 die, the probability you could have of a 4 would be 2, 2, 3, 1, 1, 3. So it'd be 3 out of 36. Y'all agree with that, class? And then, go ahead and do that. The possible outcomes, what is that? That's going to be a total of, so it's really 4 out of 42, right? For the probability of a 4 being rolled. Do you agree with this, class? And so we got and for this, that's going to be really cool. That would be 1/6. Anyway, that's the first part. Now, the second part is what? Can you just read that? Part B?
What is the probability that the sum of the dice being rolled is 4 given the coin came up tails?
All right, so it came up tails and given 4. So this is, if it came up tails, 2 die are rolled, right? I'm going to talk my way through this part of it to make sure we don't mess up. I'll tell you the common mistake on this one. For this, if a 4 came up and 2 die are rolled, it can be 1 and 3, it can be 2, 2, and 3, 1. The problem was some people used 2, 2 twice. That was what I saw in that one. Now, this is redundant. This and this are the same, but I at least understood why you would make that mistake, because you're thinking, well, 3, 1, 1, 3, those both same numbers appear 2 ways. Here you could say the 2, 2 appears this way, then switch the position. I could understand that, but that's incorrect. The 2, 2 is just the values, possible. So if you think about this, for this one, and I'll just stick with this, we've got given tails, so 2 die are rolled. What's the possibility of a 4? Since 2 die are rolled, and you look at all possible outcomes, you would have 36, class. Do you agree with that? So this is going to be simply equal to 3 out of 36 of 112. Then part C on this one.
What is the probability of 4 being rolled? Either 1 die or 2. So.
All right, so the probability of 4, here's where you use the first and second part and put them together. Probability of a 4 being rolled is going to be probability of a head, or 1/2, and a head's thrown, then the probability of a 4 being rolled would be the first one, which is going to be 1/6, plus the probability, and some people forgot to put the probability of the head or the tail in there. These are just common mistakes that I see. And then it's going to be times the probability actually occurs, which is 1/12. And that's going to be 1/12 plus, and so that's going to be 24 1/8 for that one. And part D, I don't remember what it was.
Given that the outcome is a 4, but you do not know whether 1 or 2 dice were rolled, what's the probability that the coin came up heads?
given a 4?
Yeah.
Alright, so. And I'm gonna just step back for a second before I say more. It says, if a 4 is rolled, you know that if you had one die right here, you would have a 1/6. I mean, basically, if a 4 is rolled, it's one of 4 situations here. Do you agree with this? And it can be, for this one, it can be a heads. And these, the rest of them are tails. Just looking at this as the possible event space of what can happen, if you might think of that. Does everybody follow me what I'm trying to talk about here? I'm trying to say that given the way he says a 4 is rolled, well, if you look at all the things that can have a 4 in them, you can roll 1 die and have a 4, or you can roll 2 die and have a 4. But in this case, if this is, you know, fair coin and stuff like this, these are the possibilities. Do you agree with this? Each one would be 1/4 of a chance. Do you agree, class? I'm just asking you if you follow my logic. If you do that, they want the probability of a heads, since each one of these is equally likely. Do you agree with that, basically? Then it would be simply, in that case, 1/4, wouldn't it? And I'm trying to, I want to make sure I didn't just read something here. Or, I mean, 2/3, sorry. Oh, my bad. Yeah, that's right. So, hold on for 1 second. Let's see, how is that going to come out? So, the probability of a head is 1/2. The probability of a 4 given heads is 1/6. And then probability of a 4 is 1/8. Sorry, 8/12. So it'd be 2/3 on that one. Everybody okay with that? I don't know what the average of the quiz is. But this is one of those unfortunate things that, because an early mistake affects everything, we got a lot of people that made perfects, and then we got people that kind of really messed it up because they made a really wrong mistake. And I'm going to ask one other thing of everybody. If you could, please, when you're showing work, write the formula down first you're going to use, and then put in the numbers so I can see what you're thinking. Just when there's numbers all over the place, it's really hard for me to understand what's going on. All right, next. All right. So we're into chapter 2, and for this one, just to recap it, we're talking now about probability density functions, and we've talked about the cumulative density function. I'm looking for, before I go too far afield. Did you all have a chance to look at this section? All right. I guess the best way to really see this is applied. I'm going to apply it to several problems. I have, I'm going to get through section 2-3 hopefully, and I'm going to talk about if we have a probability density function of one function, and then we bring in a second function related to the first function, how we get the probability density of the second function. Now, I'm going to ask you to be attentive here, because here's where things get a little more complicated and they get that way in a hurry. For this problem, for these things, first, by the way, are there baseball games today?
Yeah, there's one.
Because they block traffic all over. I mean, I can't go my usual route.
Yeah, I had to make sure to leave for class 45 minutes early, and I still barely made it on time. Buses are just not cutting it.
So is this because of the rain delay?
I think this one's a scheduled.
Oh,
It's because Auburn won, so they have to do the final one to decide who.
I don't know how. I know there was a rain out yesterday and it was supposed to start at 4:06, then they postponed that too because of the thunder. They had lightning in the area or something. All right, we put the density functions. We're going to do at least one of these things. I want to do a couple of these just to make sure everybody understands this. Can you get 2-2?
Yeah.
1.2. And here they have something, this is the density function. And what is it, 1/2? Or
It's 0 from negative infinity to -1.
equals 0 from minus infinity greater than x to -1.
Yeah.
And then 1/2, what is it?
1/2 plus 1/2 x from -1 to 1.
Okay, 1/2 times 1 plus x. And this is going to be from -1 greater than x less than 1.
Yep.
And then it's 1 for x
One.
greater than 1.
Greater or equal to.
Yeah, all right. Now, I'm not a big stickler for greater than or equal to. If you're a mathematician, it means a lot, but because we're engineers, we don't shave things that close. If it's greater than or equal to, or greater than in this case. All right, for this one, now these are cumulative distribution functions. Please make sure you understand this. What that means is f of x is really equal to the integral, technically from minus infinity, but you don't usually have to start there, of the probability density function f of x dx, and it would go, actually, normally what they do is prime these x's because you can't end up with anything that's part of the kernel of integration. So what this is the cumulative distribution function, and if you would go from minus infinity to infinity, it would always be 1. That is the probability of x having a value from infinity to minus infinity, basically, or from minus infinity to infinity. So if you want the probability density function, here, this is important right here, you would simply say the probability density function. Usually I drop that subscript. When you see a small f or a p with a small p, this is the probability density function. It's simply the derivative of the cumulative distribution function with respect to x. These two are interchangeable. One is an integral relationship, the other is a derivative. Everybody with me, class? Okay. Now, for this one, if you want the probability density function, you're going to have these same regions, but remember, we're going to take a derivative of this with respect to x. Follow me? I'm going to make it real clear. It'll be as obvious as anything. If you take the derivative of a constant 0, what do you get with respect to x? It's 0, right? there's no, so it's 0, and it would be from minus infinity greater than x less than minus 1. That's obvious, I think. Next, what's the probability density function when we go from minus 1 greater than x less than 1? Take a derivative of this with respect to x, what do you get? Well, it's obvious. 1/2. You agree with that, class? Has to be. So it's 1/2, it's a constant. Then anytime you go, and what I usually say is just else, any other part of the possible values of x, this is going to be 0 as well, because this value is 1, you take a derivative of it, you get 0. Do you follow me, class? Now here's the one thing I'm going to tell you, you got to be careful. I'll get to some examples of this. See, these are all continuous, and the f of x has to be continuous. It does. But if it's continuous, and I want you to think about this, suppose I had, he doesn't cover it in the book yet, but I want you to make sure you see this. Suppose my okay, I'm trying to do this. We're going to have something where f of x starts at 0, then it goes to 1/2, then it goes to 1. This is going to be capital F of x versus x. Call this 1, call this 2. Follow me? Now, you know that small f of x, the probability density function, would be a derivative of that. And this value, well, what happens? This is really a u of x function times 1/2, right? It's u of x minus 1, and it's weighted by 1/2. When you take a derivative of a step function, what do you get? Derivative of u of x with respect to x, class? It's an impulse, right? And the weight of the impulse is going to be actually going to be 1/2, and it would be a delta. In this case, it would be x minus 1. Here, you'd also have an impulse function, and it would be 1/2 delta of x minus 2. I'm making you aware of that because oftentimes people will forget that when there's a discontinuity at a point, it actually results in an impulse. Fair on this one, class? Now, if you integrate this thing, when you integrate through an impulse, then you get a u of x. So it does work, going backwards or forward. All right. So that problem, anyway, this would be the density function. What else does he ask for that one?
Found the probability that x is equal to 1/4.
All right, I want you to hear that. Remember, 1/4 is in this range, right? He's asking the value. This is not a discrete set of events. This is a continuous. What's the probability of it having exactly 1/4 as a value? It's 0 because it's a continuous thing, right? Because it's continuous. If you take the value of the probability density function, 1/2 times dx is x goes to 0, you get 0, right? Because dx, in the limit as dx goes to 0, you get 0. Do you follow me? But if it was an impulse function, you wouldn't, right? So if I asked you the probability, I erased it, but the probability for this one, that x was equal to 1, what would it be? Do you remember? 1/2. Follow me? In any other value, the probability is 1/3 here, that the actual, less than 1/2, I should say. Anywhere less than 1/2 is 0, because 1 at the point, not half, less than 1 is 0, because at 1 is where you get that discontinuity, and at 2 you get the second discontinuity. Makes sense to everybody? Here's what I'm really trying to say. If you look at that density function, the cumulative density function, f of x versus x, the way I drew it was this. And this is 1/2. This is 1, this is at 1, this is at 2. So the probability that x could be anywhere between 0 and 1 is absolutely 0. As a matter of fact, it's 0 all the way down to minus infinity if you want to be clear and extend that. anywhere between 1 and 2, it's exactly 1/2. And anywhere between 2 and above, it's 1. It has to be a value, I shouldn't say, sorry. The value of x anywhere over here or less than that would be equal to 1. The value of x here or less than there would be 1/2. And the value, or the probability of x being in this range or less would be 0. Okay. That said, is there another part to that question?
Yeah, there's two. Find the probability that x is greater than 3/4.
All right, if you look at this right here for this one, here's my density function. I want to make sure you can visualize this. This is the probability density function, f of x, and it's basically going to be 0 until you get to -1. Actually, let me do this. Call this f of x. This is going to be -1, this is 1, and it's got a value of 1/2. And since that's the probability density function, and you're asking the probability that x is
Greater than 3/4.
greater than 3/4, so 3/4 is right here. What we're really talking about is the area that I just checkered off between 3/4 and 1, right? If you look at that, I mean, there's a couple ways to do it, but probably the easiest, and this is the way I always do these problems, the probability of x being greater than 3/4, less than 1, is really going to be the integral of f of x, which happens to be 1/2, thank God. And it's going to be times dx from 3/4 to 1, and that's simply going to be, well, 1 minus 3/4, it's going to be 1/4 times 1/2 or 1/8. Do you all agree with this, class? This is a very simple example, but I'm trying to make sure everybody sees this. What's the next part of that one?
Find the probability that -1/2 is less than x, which is less than or equal to 1/2.
The probability that minus what?
1/2.
Greater than x, less than?
Less than or equal to 1/2.
All right, less than or equal. Now, how would you do that? Just think about this. What were we talking about now? Oh, but this is 1/2, right? Minus 1/2, I should say. And this is 1/2. The probability that x is between these two values would be 1. It's just the area under this curve. You agree, class? Right there that I've checkered. Can you all see that? It's got a width of 1, a height of 1/2. It's 1/2. With me on this? These are easy. You can eyeball them. So this is just going to be equal to 1/2 times, I'm sorry. This width here, from -1/2 to 1/2 is 1. The height is 1/2. It's a simple rectangle, so it's going to be 1/2. Is there another part?
That's it.
Now, that's an extremely simple problem, but I start simple on this one because this thing can get, and it will, get much more complicated very shortly. Take a look at the next one. Yeah, I want to do 2-2.32. How many did that? One person? Did you do it?
2.3?
Yeah, okay. All right, I want to do that, but I'm going to tell you, there's a typical mistake in this one when you're doing this that will trip you up. Actually, a lot of these problems, you kind of get almost relaxed, thinking I've got it, and then there's one subtlety that throws everything out. All right.
Is this describing the exponential?
Pardon me?
Is this describing exponential?
Yeah, EXP.
Yeah.
Anytime you see EXP, he means x like e to the power.
Okay.
Give me 1 second though. Okay, go ahead.
F of x is equal to a times 1 minus e.
This is 2-2.3.
Yep,
F of x is what?
equal to a times 1 minus e.
Oh, capital A. Capital A's, go ahead, I'm sorry.
1 minus e to the negative x minus 1.
Minus the quantity x minus 1
Yes.
times.
From 1 less than x less than infinity.
All right, so u of x minus 1. That's the way I usually write this. That u function doesn't turn on until the argument inside there is 0. And that would be when x is 1 or greater than that. That's an easy way to do it. Do you all agree, class? Now what this really is a skewed exponential that starts really at 1. Because when it's 1, you get 1 minus e to the 0, or 1 minus 1 is 0. Do you follow me? So this is the density function. But is that capital F or small f?
Capital F.
All right, so sorry, this is a cumulative distribution function, my bad. And that's all you need to describe it. We could have the two regions. Do y'all agree? Now, he asks the value of A that would make this legitimate. What's the one thing about a cumulative distribution function that you know for sure?
The limit as x goes to infinity is equal to 1.
1. When x goes to infinity, in the limit as x goes to infinity, f of x has to go to 1. And if you look at that, that means that would be a, and it would be 1 minus 0, because e to the minus infinity would be 0. Do you agree with this, class? So you got a right there has to be 1. Has to be 1. Then, what's the next part?
What is f of x at 2?
Small f of x?
Large f of x.
F of x what?
F of x at 2.
Okay. All right, so this is almost. So if I want f of x when it's equal to 2, what's that really going to be since a is 1? Is 1 minus e to the 2 minus 1 is going to be 1 e to the minus 1. Do you agree, class? I don't know. Does he give an answer for that? It's like 0.6 something.
632.
632?
632 is what I got.
You're right. It is, but you understand that, right? And there's, what's the next part? That almost sounds too easy.
What is the probability if the random variable lies in the interval 2 less than x less than infinity?
Okay. Now, I'll tell you, we could use capital F of x to do that. Remember, that's the probability of a thing being the value of x or less than, right? So if he wants the probability it lies between when?
2 less than x to infinity. From 2 to infinity.
All right, so here he wants the probability, and you started with minus 2, was it?
No, it's just 2.
2 greater than or equal to x, less than or equal to infinity? Is that right?
Yeah.
Okay. Well, if you think about this, and remember what that cumulative probability, or cumulative density function says, we know at infinity, the likelihood it has a value infinity or less is 1, right? And if you subtract from that the value, that the probability has a value of 2 or less, then you would get the range between 2 and infinity. Do you agree with that? This is one way to do it. So this is going to be really the density function at infinity minus the cumulative distribution function at infinity minus cumulative distribution function at 2. And in this case, it's 1 minus, and then that thing at 2, which we've got right here, would be 1 minus the quantity 1 minus e to the minus 1. Or in this case, it's just going to be e to the minus 1. And that would be the probability between 2 and infinity. That's one way to do it. Now, I'm gonna tell you a smart way to do these things so you don't trip up sometimes when they want the probability between like 1 and 3 and 5 and 7. In other words, cumulative. Let's get the density function. So I'm gonna do it right here, and I know I'm gonna, or right here. I know they're gonna ask for the density function. So if I want f of x, I know it's the derivative of f of x with respect to x, right? Now I want you to take a look at this for a second because this is important. This switch right here turns it on for x 1 or greater, correct? That means if I take a derivative of this, I'm going to have to include something that makes that happen as well. Do you agree, class? If I just look at this and I take a derivative of this, I'm going to show you how I write this so I don't make mistakes. I'll just do, I know f of x, I know a is equal to 1, is equal to 1, and then what I'm going to do is have minus, and I'm going to separate these two values. So I'm going to have e to the 1, which is a scalar value, then I'm going to have e to the minus x. Follow me on this, class? If I take e to the minus x, and then e to the minus 1 is e to the 1. E to the 1 is a constant. You don't have to do it this way, but for me it makes it a lot easier. So this would be the cumulative distribution function, and it really would be for x greater than or equal to 1, less than or equal to infinity. Do you agree with that? Everybody? All right, now I take a derivative of this, or sorry, my f of x, small f of x, would be equal to the derivative with respect to x of capital F of x. And that's just going to be e to the 1. There's two minus signs times, so they'll cancel when I take a derivative of e to the minus x, and then I get e to the minus x again. And this is still valid for less than or equal to infinity. Do you agree, class? Everybody with this? Now this is what I like doing here. So this is my f of x. I'll put it over here. For this one, okay. Now read that part again.
Part C or part D?
C for starters.
What is the probability if the random variable lies in the interval x less than, or x is greater than 2, which is less than infinity?
All right. For this one, well, we did that way, but we could easily say the probability of x greater than 2 and less than or equal to infinity would be equal to the integral from 2 to infinity of e to the 1, e to the minus x dx. Breaking out that e to the 1 will take care of some problems you get when you're trying to integrate e to the minus x minus 1. This is my experience, at least, with this stuff. And this would be e to the 1, and then you're going to get it's just going to be e to the minus 2, or it's going to be e to the minus 1, and that's what we got before. Do you agree with that? That's using, I'm simply doing the integration of the density function, even though they're mathematically the identical thing that we did with the cumulative distribution. That's part C, and then part D.
What's the probability if the random variable lies in the interval x greater than 1, less than or equal to 3?
Now here I'm going to use the density function for this part. And if you look at it, this one, the probability density function, I'm just going to integrate from 1 to 3, the density function, which is e to the 1, e to the minus x dx. And you can see this breaking this thing out will prevent some mistakes that happens when you do an integral of e to the minus quantity x minus 1. People will make mistakes with that. At least that's been my experience. So if I do this, I get e to the 1, right? Then I get e to the minus x, or minus e to the minus x, but I reverse the order, so I'll take the 1 up top, 3 in the bottom, and then I get e to the minus 1 minus e to the minus 3. I'm just doing integration. Then what I'll do is go ahead and multiply through, so I get 1 minus e to the minus 2. And that's part B. That's a very small number. You have it? I think it's in the solutions, but I don't remember what it was.
Yeah, it's gonna be 0.864.
0.0864?
You said 1 minus e to the negative 2?
Yeah.
Yeah, it's gonna be 0.864.
Oh, yeah, all right, that's right. 864. That's right. Agree, class, for this one? All right. Erase this, get to the next one. These are very obvious, but the next part. Let's see. So when I go into how many tried 2-2.4? Did you do it? All right, I put the solutions, and we're gonna go through, this is the last one in this section, then we're gonna get to the next part. Now, I'm gonna tell you about this problem. This is the kind of problem you might get on a quiz. I mean, this level of complexity. So for this one, can you help me out with what he gives? Capital F of x
Capital F of x
equals
0, x greater than negative infinity, less than or equal to negative 2. And then a times 1 plus, and then you scratched out cosine with sine.
It is sine of bx.
X is greater than negative 2, less than or equal to 2. And then 1 from x greater than 2 to infinity.
Okay, that's it. Now, this is where you have to understand what you're dealing with. This is a cumulative distribution function, and they want the values for A and B, correct, class? So the first thing you have to take a look at is in the limits, if you have this kind of a function right here, we know it's 0 at -2. It's something, I hope I said this before, but f of x has to be continuous. It cannot have discrete jumps. Do you follow me? It is a continuous function, uninterrupted. And if you look at this for a second, if this is f of x versus x right here, if it's continuous up to -2 right here, that's -2, it's 0. It means it has to be 0 just on the other side of -2, or this has to be 0 when x is equal to -2. Does everybody agree with that, class? So I'll come over here and I know that f of x equals -2 has to be equal to 0, and that's equal to a times 1 plus sine of bx. In this case, it would be -2, or -2b here. And that means, just by looking at this, that sine value has to be -1. So I say that sine of -2b is equal to -1. I'm just stating, I think, the obvious. Agreed, class? All right, now, after that, sine is 1 at pi over 2, when sine of theta is 1 at theta equals pi over 2, and it's minus 1, right, or I should say, the sine of minus pi over 2 is minus 1. Do you agree with that, everybody? I'm going to write it down. So the sine of minus pi over 2 equals minus 1. I'm going to try to show you this. This is sine of x versus x. It does this basically. It's an odd function, is what I'm trying to say. I think it's only right. So if you look at this, that means minus pi over 2 has to be the argument of minus 2b, and that means b is equal to pi over 4. Making sure everybody sees this. Correct, class? Now, the next part is, if you look at this, right here, when the density function, when it goes to 2, when f of 2, not minus 2, this has to be 1 because it's got to be continuous. So just before we enter this region, this entire quantity has to be 1 equal to this. Do you follow me, class? It has to be continuous. Okay. So now we come here and we say that f of 2 has to be equal to a, and we have 1 plus, well, now we have the sine of, right here, it's going to be the sine of oh, I'm sorry. Plus, sorry. Sine of 2 times pi over 4, or that's the sine of 90, and that's going to be equal to a times 2 would be equal to 1 because we're at, in this case, x equals 2, and that means a has to be 1/2. Do y'all agree with that for this one? It's just a matter of solving it. If you know when you actually get the value here at 2 and 2, it has to be continuous, so the value of that cumulative distribution function has to be 1. Do you agree? Yes, sir.
Does the Scotland problem like matter with the boundary conditions, like less than or equal to on this type of
The
problem?
only thing I use those for is, just before the break, before x equal to 2 or less than that, has to be equal to f of x, capital F of x has to be equal to whatever it is on the other side, and it's 1. Now, you use that sort of like matching boundary values, but that's the way you do these kind of problems. Anyway, you got a half for that. Then what did they ask for? I mean, did I answer your questions?
Yes, yes.
Find the probability that x is greater than 1.
All right, now, when you look at that, probability of x greater than 1, you can do it using this, or you can get the probability density function and then integrate it. But for this one, the probability of x greater than 1, let me do it right over here. x greater than 1, less than 2, you might say. Well, really, or it could be less than infinity. That would be equal to it would be equal to 1 minus the probability of, in this case, x less than or equal to 1. Do you agree with that? We're just making an obvious thing, correct? So for this part right here, you got 1 minus, now that is the definition of f of x right there. So f of x equals 1, and that's 1 minus, and a is a half, isn't it? Yeah. So it's going to be 1/2, and here you're going to have 1 plus the sine of pi over 4 times 1. That's 1/2 times 1 plus the sine of 45 degrees, and that's 1 over square root of 2. And I don't know what that is, but you can see that's mathematically correct. Follow me? The number, he probably gives you a number for that. Does that make sense to everybody? You're just evaluating this right here. Oh, but you're going to have to subtract 1 from it. Sorry. You're going to have to take 1 minus 1/2. Then you're going to have 1 plus 1 over the square root of 2. And that should be the correct answer once you do the math on that. And I'm certain it is. What else? I mean, does everybody follow me? I'm trying to get through this, but go ahead.
Find the probability that x is negative.
Okay. Now, if you look at this probability distribution function right here, if you draw it up, you're going to see something. I mean, this is the probability density function. I'm sorry, it's the cumulative distribution function. My gosh. Probability that it's equal to, x is equal to 0 or less than 0, right?
It just says negative.
All right, well, negative would be down here if this is 0. And that really is going to be what? F of 0, follow me? Because that means anywhere down here, that would be the probability, cumulative probability of it being there. And that would be exactly 1/2. Can you see it? You can put it in the numbers, right? Because here, if you put in, here, if you put in x equals 0, sine of 0 is 0, you get 1. 1 times a is a half, you're going to get 1/2. Agreed, class? On this? All right. The rest of the problems in section 2-3.1 are really taking the prior problems in section 2-2 and just taking derivatives of the probability density function. You guys tried that, right? I mean, that's not hard, I don't think, that part. What I'm going to do now is talk about what happens if you got a density function for some variable, and then you have a function that uses that variable. How do you get the density function for the other? This is trickier right here. This kind of a problem you can fumble it in different ways, but primarily because you're not being attentive to what the boundaries are. That's usually the way you make mistakes on that kind of problem. Typically. All right. Let's see. This is part of section 2-3, but I want to be real clear about this. If you have a density function, call it f of x, right? you've got some density function. Obviously, it's related to the variable x. All right, and they call it the random variable, always have capital letters. Small variable x indicates an actual value. But if you look at this as such, suppose you have another function. Suppose you have y is equal to some function of x, call it g of x. And you want to find out, your goal is to find out what the density function is in terms of y. So they want to know that. Remember, we've got this, so we know the density function of x, and now we're looking for the density function of y. So the way he talks about it here, it's smart to read this part in section 2-3. This is on page 61 and 62 in that PDF I posted. Cooper, no, McGill. So what he says first, let's take a look at what can actually happen and try to get a visual representation of what's going on. If I have x, and I'll call this g of x. If you take a look at that, I'm going to try to just draw something representative. It doesn't matter what it looks like. But if I have a value of x here, and then I have a value of x plus delta x, or I'll say dx. So this range. If I look up here, I have a value of g of x, and then I have a value here of g of x plus delta x. Now, what I'm really trying to do is say the probability of the value of x being here, or f of x times dx. Follow me on this, class? That probability is the same as the probability that g of x is between here and here. Now this g of x we really call y. It's a different variable. Follow me, class? So if you look at this, that would be equal to really y times f of y. And in his book, I'm going to try to make sure I keep this on track with what he has in his book. It's going to be f of x dx is going to be equal to fyy dy in a second. But the way he shows it, this is dy. I'm going to write it here. So f of x dx is equal to f of y dy. Now really, I'm trying to say is the probability it's here in x is the same as the probability it's here. It would be f of y dy. And this, actually, I can just make this dy thick. And there would be an f of y. Now that's going to be true generally. At least can you follow me what I'm saying here? A couple examples will make it clear, but I'm going to tell you there's one trick with this one you got to be careful. about, and I'll show it to you in a second. Can you have this? Now you can say that f of y is really equal to f of x. And then what he's going to have is d dy of x. So it's going to take a derivative of the function x with respect to y. I'm going to give you an example, a couple examples, and try to work through this and show you. Now this is the thing that people are going to have trouble with when you get functions that are strictly positive, like y equals x squared. X squared is strictly if y equals x squared, y is strictly positive, but x can have negative and positive values, so it's going to change how we represent this f of y. And you'll see this in a second. The example he does in the book, that I have in the notes, a bunch of stuff on this. Here's one. So I'll do that. I think I can do it right here. If we have f of x is equal to e to the minus x u of x, put it that way. Yeah. And then he says y equals x cubed. Now, again, anytime there's a capital letter, it just means it's a random variable. Now that's an odd function, if you look at that. This won't trip us up, but if you look at this, first I'm going to say x in terms of y is going to be simply y to the 1/3 power. Does everybody agree with this? Now, if you got that, am I over? I don't think I'm over.
What is the thing on the top said? It's negative x.
It's e to the minus x u of x. It's only good for x equals 0 or greater than that. That's the only thing I was trying to say. In other words, it's strict positive. But if you look at this right here, remember, if x is, or y is x cubed, x is y to the 1/3. Now go over there and find, we want f of y, so the density function f of y here would be equal to, technically it's f of x times dx dy. What we're going to do is put f of x there, but instead of x, we'll substitute y. All right, so it'll be a function of y. Here's f of x. So I'm going to have e to the minus, and x is going to be really y to the 1/3 power. So I've replaced the x there by y to the 1/3 power. It's the only thing that I'm doing right there is replacing it. Then I have to take the derivative of x with respect to y. If you take a look at that, derivative of that x with respect to y is going to be 1/3, and then it would be y to the minus 2/3, or 1/3, 1 over y to the 2/3 power is another way of writing. Do you agree with that, class? I mean, can you all read it? Okay. If you take that, I put it down here, so I have that. It's going to be times 1/3, 1 over y to the 2/3 power, and that's the density function for f of y. And you could prove one thing. If you take this and integrate it over possible values of y, remember, x has got to be 0 or greater than 0. If x is 0 or greater than 0, it means y has to be 0 or greater than 0 as well. So if you integrate this density function from 0 to infinity, you will get 1. All right, just like if you integrate this from 0 to infinity, you will get 1 as well too. Okay. So that's interesting in itself, with just a simple application to a simple problem. Here's where it gets a little tricky. If now I actually have something where we have an even function. And I'm going to show you this one. So if we have y equal x squared, all right, take a look at that. That's this function. Right? And you take a look at this, x here is going to be equal to plus or minus the square root of y. Y'all follow me in that class? It could be either. Both of them will solve it. So when you're trying to do the density function, this one, you have to account for both the negative. Remember, y will never be negative, but the probability pattern, let's see. If you take a look right here of the probability that you have f of y dy, it is associated with the probability you have f of x dx, but also here you would have f of x dx associated with that. In other words, if you have a value of the probability of y is between, is basically in there, is the same thing as the probability of x being here or here. I hope you see that. Does that make sense, everybody? Because it's not a monotonically changing function like that. And the way you're going to have to do that, and the way he does it in the book, accounting for it, by the way, this is on page 62. Try to do this right here. So f of y in general is going to be f of x times dx dy. But because, I mean, in fact, what it has to be is going to be the absolute value of this. You're going to end up with f of y is going to be equal to this one, and this then would be the magnitude of the x dy, and that would be f of square root of y plus f of minus the square root of y, and then the magnitude of dx dy is 1 over the square root of y, and this would be f of y. Now, put sub x there. These are the density functions for x. This is going to take a little time to think about and explain, but because it's really because that there's two values of x for any one value of y. That's the reason for that. Maybe you see this better if I use a couple of different examples with this. I didn't get to the exercise 2-3.1 or 2-3.2. You can read through that and take a look at it and do problems in the back. But here's what I'm gonna do next time. I'm gonna ask you to take a careful look at what I just put up there and look at the book, and then I'll give you some problems, but try to read through section 2-4.2, and I'll put that up there. We're gonna get into expected values, standard deviation, and how all are related. I didn't get there today, but I will next time. It is 11:02, isn't it? Are there any questions about this? This is going to be a little harder to see because you almost have to play with it. You have to understand that the probability of X being here or here is the same thing as the probability of Y only being here. So you account for both of those places. You have to. That's the bottom line of this because it's not a monotonically increasing function. And the book doesn't do a bad job. All right. I'll see you next time. I'll put up stuff, but if you have questions, just stay after. And I think I got either an infection or bleeding in my